Okay, in our previous video, we looked at some simple reactions involving monosaccharides, but today we're going to get into some more complicated ones involving chain lengthening and shortening. First, we're going to start out with chain lengthening. It's not very common to do this anymore simply because you can buy most custom carbohydrates. However, this was referred to as the Kalani-Fisher synthesis. And it was used for a while, especially when chemists were investigating the overall structure and conformation of carbohydrates in the early 1900s. And the overall mechanism looks something like this. And what I'm going to do is I'm just going to abbreviate my carbohydrate like this with an R group. And that R group, you can imagine, is the lower half of my Fisher projection. So this is an example of an aldose, right? We don't necessarily know how many carbons it is, but that doesn't matter. And in this chain lengthening reaction, what we're going to do first is react it with hydrogen cyanide. As you can tell, this is a very toxic, dangerous reaction, but back then they were a little bit more cavalier. And then in step 2, you treat this with hydrogen gas, and then you use a special metal catalyst. You use palladium, you use barium sulfate, and you use water. And that helps to reduce the reaction in the final step. All right, so let's take a look at our products. At the end, we're going to add a carbon, and that's going to be one of our crossbars here. The R group is still going to stay put, and we'll get an OH and a hydrogen. The problem with this is we'll actually get both, where you can have the OH on the left and on the right. So we get two different products out of this. And if we look at these would be an example of epimers, meaning they're diastereomers that differ only at this top stereocenter. So this top stereocenter is different for both of these, but the rest of the stereocenters are going to be exactly the same in that R group tail underneath. So let's take a look at the mechanism. And luckily the mechanism uses a lot of chemistry that we've seen before involving aldehydes. And in the first step, what we're going to do is we're going to have our aldehyde react with the hydrogen cyanide. So in this case, we've got HCN. We're going to protonate this oxygen on our aldehyde. And we're going to make this aldehyde into an even better electrophile by protonating it. And then we still have this Cn- floating around. So this Cn- is just going to attack in and kick up electrons onto that oxygen. Now when we do this, we could attack from either the top face or the bottom face, and that's really important to remember here. So what's going to happen is we're going to get this triple bond, but the OH group could either be on the right or the left. And what I mean by that is this OH group could be on either side. We really have no control. All right, and let's show our epimer over here. And we still have this carbon-nitrogen triple bond. If you remember back to our aldehyde chapter, this is called a cyanohydrin. That's when cyanide attacks into our aldehyde. All right, so now what we're going to use is we're going to use our step 2 catalysts. And what that's going to do is it's going to reduce that triple bond to a double bond. In fact, this is pretty much the same thing as Lindlar's catalyst. It's that poison catalyst that we used with triple bonds to reduce them to double bonds. And when we saw this reaction done with alkynes, so carbon-carbon triple bond, we were able to get cis alkenes out. But in this case, it doesn't really matter because our nitriles don't have any sort of regiochemistry. We're not going to get cis or trans. But let's take a look at what we get out. So if we reduce that triple bond to a double bond, it's going to look like this now. So we can imagine both of those adding in. We can also imagine our epimer over here. And when we look at this, we've converted our cyanohydrin all the way over to an imine, right? So in this case, we've got that carbon-nitrogen double bond, like we saw in our aldehyde chapter. All right, so now that we've got our imine, we can hydrolyze this using H2O. I'm not going to go over this whole mechanism, but if you remember, H2O and any sort of acid catalyst will quickly tautomerize these imines, or I shouldn't even say tautomerize, hydrolyze these imines back into their aldehyde form. So we're going to get two new aldehydes out, one where we've got an OH group here, and one where we've got an OH group here. Like I said, these reactions typically aren't done very commonly anymore because you can just buy most of these carbohydrates commercially, but it is a unique way of adding one more carbon onto an existing aldose. So in this case, this carbon right here that we've added, oops, sorry, not that carbon. This carbon right here that we've added in was originally the carbon that was in the cyanide right here. So we're able to add in one specific carbon that way. All right, so this was called the Kalani-Fisher synthesis. Again, a lot of history here, and it adds a carbon in, but is there a way to remove a carbon? And that's what the next reaction is going to look at, and that's going to be called chain shortening. And this is called sometimes the wool degradation. And the wool degradation is kind of the opposite. We want to take one of those carbons and we want to pluck it off. So let's take a look at this reaction. And in this mechanism, we're going to start with an aldose again, and I'm just going to pick an aldose that's pretty simple. Again, I'm just going to put an R group tail on there. It doesn't really matter the R group, but the goal is to remove one of the carbons from this. What we're going to do first is we're going to react this with a nucleophile. And if we think about which site's more nucleophilic, the nitrogen or the oxygen, it's important to remember that nitrogens are more nucleophilic than oxygen because they hold on to their lone pairs less tightly. So in this reaction, this nitrogen is going to act as the nucleophile, react with the aldehyde, and we're going to form an imine. I'm not going to do this full mechanism right now because we already did that a lot in our previous chapter on aldehydes. But we would get a structure that looks something like this. And as you can see, we've got this imine double bond. Oh, actually, I shouldn't have a hydrogen there. Sorry about that. We've got this carbon-nitrogen imine in here. However, we also have this OH group kind of dangling off the end. And because of that, we call this entire functional group something else. We call this an oxime. It's a special type of imine. All right, so we've got this oxime on there. And then in our next step, we're going to react this with a mixture of different reagents. Let me make this shorter. We're going to react this with acetic anhydride. We're going to react this with sodium acetate. And we're going to react this with acetic acid. Essentially, this is going to create a buffered system. By doing that, what we're going to do is we're going to react the acetic anhydride with this OH group coming off our oxime, and we'll acylate it. Luckily, it's the most reactive OH group on this molecule, so we can selectively acylate it as long as we pay attention to our stoichiometry and we don't add excess acetic anhydride. So we're going to acylate that group. And like I said, this is sometimes just abbreviated as AC. So sometimes you see this written as OAC. You're welcome to draw it out though, if you'd like. And we still have the sodium acetate floating around, which is just that carboxylate salt. So really what I'm saying is this is the same as this down here. So we've got this, and it's a really weak base, but it's good enough for this reaction. What it's going to do is grab this hydrogen, or proton I should say, clamp down, and it's going to kick off this entire group right here. And luckily this entire group is a pretty good leaving group because once it's kicked off, it's resonance stabilized. And our product that we make, looks pretty familiar. It looks a lot like the reaction we saw above, where we've got a cyanohydrin. Whoops, this should be an OH group. So we've created our cyanohydrin. But in this step, we can actually kick off that nitrile by using a base. So what we do in the second step is we use a really strong base, or actually this would be the third step, and when we do this, we're going to pluck off this proton over here. We're going to clamp this down, and we're going to kick off cyanide as our leaving group. And when we do this, we're going to create our new aldehyde, and we kick off our cyanide, and by doing this, we've got loss of a carbon. The good thing with this reaction is you're not going to create a mixture of epimers. You're only going to make one product, right? Because we're not scrambling or creating a new stereocenter. We're just lopping off a carbon altogether. Like I said, these reactions are pretty old school, but I think the history behind them is pretty interesting. The fact that we're actually able to create and customize these carbohydrates at will to have the appropriate number of carbons that we want. All right, good luck studying.